In this video, we're going to look at combustion and what it can tell us about relative stability, and we're going to look at redox reactions in organic chemistry. Okay, when an alkane is treated with oxygen, and under ideal conditions, the alkane is completely converted to carbon dioxide and water. Okay, and this is what we call complete combustion. This is giving as much oxygen as the system will take. Okay, now you may notice that this equation is not balanced. This is because I can't generally balance this because 2n plus 2 over n is not a reducible fraction. Okay, combustion is always exothermic, and delta H is a negative number. Okay, so delta H equals a negative number. All right. Now, when a cycloalkane undergoes a similar combustion reaction, we can reduce the fraction because this is a reducible fraction, and we can give a general equation now. So CnH2n plus 2 plus 1.5 moles of O2 produces an equivalent number of CO2 molecules and water molecules. All right, so the combustion all the way to CO2 and water is what we call complete combustion. If there's not enough oxygen getting to the system, that we can get incomplete combustion, producing carbon monoxide in some cases or carbon in others. Okay, this incomplete combustion is often associated with poor engine performance in cars. Okay, so recognize that alkane combustion is the predominant process that is moving automobiles in this country, and that we get the most energy from the complete combustion reaction at the top. The incomplete combustion is not as energetic. Plus, carbon monoxide is a toxic compound. We don't want to generate too much of that. Carbon itself is basically soot, and it coats on the side of the smokestacks and is kind of a nasty byproduct of combustion. All right. So in the nomenclature session of this chapter, we noticed the word octane, and prior to studying organic chemistry, most of you had heard of octane before. It's how gasoline's quality is rated. Okay, all right, so here's what octane number means. In heptane, it's assigned as an octane number of 0, and it causes severe engine knock. Isooctane, or 2,2,5-trimethylpentane, is assigned an octane number of 100, and this leads to minimal engine knock. Octane number is how rapidly does it ignite relative to N-heptane isooctane mixtures. All right, and actually we want it to ignite slower, I believe, because we don't want it to burn before it gets to the combustion chamber. All right, so it's not practical to just run America's transportation system on ultra pure 2,2,5-trimethylpentane. That would be prohibitively expensive, and it would be hard to ever generate enough of that to do the job. Okay, so what's done is we take petroleum fractions and add anti-knock compounds that make not so great fuels burn the way isooctane burns. Okay, so some anti-knock compounds that you may have heard of, or the first one was tetraethyl lead, which was banned in 1974. This is because we're basically raining lead oxide down on America every time you burned, or every time you drove your car, you were raining lead oxide down in your neighborhood. Okay, methyl cyclopentadienyl manganese tricarbonyl is a replacement. I think it's still used in Canada. It generates manganese as a byproduct, which is a far less toxic metal than lead. For a while, this compound, methyl tert-butyl ether, was the predominant anti-knock compound, but it was discovered that some people were sensitive to it. Now we're using ethanol or benzene are the most common anti-knock compounds used now. Okay. All right, so we can get a lot of information about relative energy from combustion reactions. All right, so here is the first example of something we call a potential energy diagram. We're going to look at how does the energy of the system change as a reaction progresses. On the y-axis, we have energy, usually in kilojoules or kilocalories per mole. I'm going to use kilojoules because the textbook uses that, but it's not universally adopted. Okay, or not everybody has changed from kilojoules to kilocalories. On the x-axis, we're just going to look at the progress of the reaction. These units are ill-defined. Basically, on the far right, the reaction's over, and on the far left, it is just starting. All right, so here is a typical potential energy diagram for an exothermic reaction like combustion. We're going to find that there's really, in many cases, they're more complex than this, but this is the simplest type of situation. All right, so we have reactants over here on the left. We have products over here on the far right. The energy of the products minus the energy of the reactants is defined as delta H or delta E. In organic chemistry, we don't make as big a deal out of the difference between delta H and delta G. We'll find a few cases where that's an important consideration, but for now we're just going to focus predominantly on delta H. All right, so if products are lower in energy than the reactants, this is a negative number. Negative number is associated with an exothermic reaction. The reaction produces heat. All right. Okay, so as reactants transition to products, they don't smoothly go down a hill. Actually, it usually requires some what we call energy of activation to get the reaction to go. Okay, so here is a typical situation. So at some point along the transition point, we're going to have a maximum energy. This energy here, the maximum energy along the way, is referred to as the transition state. And the energy difference between the reactants and the transition state is known as the energy of activation, which really affects the rate of the reaction. And that's something we're going to discuss more detail in a couple of chapters from now, chapter 4, when we actually talk about reactions. All right, so this is fortunate for us that that reactions work this way, right? Because if not, imagine pumping gas at the gas station. If it wasn't for this activation energy, it would spontaneously burn as it came out of the gas pump. Okay? All right, so we know that we have to add some activation energy with a match or something like that to actually get a combustion reaction to proceed. All right, so that is an exothermic reaction. Up here we have an endothermic reaction, and the difference here is that the products are higher in energy than the reactants. Okay, So we have to put heat in the system to make an endothermic reaction proceed. Okay, and these also have activation energies as well. Most of the reactions that work, however, are exothermic. Okay, and we're going to see many examples of exothermic reactions as we proceed in this class. Okay, so let's look at how we can use heat of combustion to determine relative energy of the system. Okay, so let's take two compounds that are isomeric. We're going to take N-hexane here and 2-methylpentane right here. Okay, because they're isomeric, they're both C6H14. Their balanced equation is the same. Regardless of what the structure of C6H14 is, it reacts with 9.5 oxygens to make 6 CO2s and 7 waters. Okay, these compounds, however, have different heats of combustion. The heat of combustion, or delta H for the combustion reaction, is negative 4163 kilojoules for N-hexane, and for 2-methylpentane, it's negative 4157. All right, so we're going to use this quantity here called heat of combustion, or it's called delta H of combustion. This is how much heat was generated from a combustion reaction. Basically, heat of combustion is the negative of the delta H for the combustion reaction. The proper thermodynamic equation is a negative number, but we're looking at how much heat did we get, so that's actually going to be reported as a positive number. Okay. All right, so we see that the delta H of combustion for hexane is 4163, and it's a little bit lower for 2-methylpentane. All right, so they're both producing the same set of products, okay? The CO2 and water, there's no isomers for those compounds. They're the same compounds produced independently from each of these two sources. Okay, so hexane starts out at a higher place than does 2-methylpentane, okay? And we look at this difference between them as being 6 kilojoules per mole. So that we're going to now say that 2-methylpentane is lower in energy or more stable by 6 kilojoules per mole compared to hexane, okay? And here's a relationship I want you to remember. More stable correlates to something that's lower in energy. Okay, and less stable, just the opposite. It implies something that's higher in energy. Okay, and that's an important relationship to remember. Okay, this puny little difference here is exaggerated quite a lot in this diagram. Okay, you can tell this diagram is not to scale. The magenta line and the blue line would really be right on top of each other if it was. But branching is a stabilizing structural influence. It's not a really big one. This is the first thing that we'll take up in organic chemistry that affects relative stabilities of molecules. So branching is stabilizing, but not very stabilizing. We're going to see things later in the course where the relative energy difference is a lot greater than 6 kilojoules per mole. All right, so combustion is an oxidation reaction. CH4 goes to CO2. That represents oxidation. CO2 going back to CH4, that represents a reduction reaction. So how do we define oxidation and reduction in organic chemistry? All right, there's a lot of ways to define it. Oxidation is a gain of oxygen or a loss of hydrogen. Reduction can be a gain of H2 or a loss of oxygen. A lot of reactions are not redox reactions also. A gain or loss of water, ammonia, or hydrogen fluoride are the analogous compounds underneath it in the periodic table are not redox reactions. They're we just describe them as not being classified as redox. Okay, but these definitions here are really hard to universally apply to organic compounds. So we have to develop a way to determine whether oxidation or reduction is happening. So if you can't do it the easy way by seeing obvious gains in oxygen or hydrogen or losses of oxygen or hydrogen, you have to go through a series of assigning the oxidation states of the carbons that are involved in the reaction. And that's the only way you can tell whether it's oxidation, reduction, or neither. Okay, so how do we do that? First, we have to assign the oxidation state at carbon. So number one is we got to pretend, and this is a big pretend here. We're going to pretend that all of the bonds to carbon are ionic bonds except for CC bonds, and we're going to keep those as covalent bonds. We're going to give a +1 to each hydrogen, okay, or any other element that's less electronegative than carbon, and we're going to give a -1 to each halogen or each singly bonded O or N group, or the elements underneath them. We're going to give a -2 to each doubly bonded oxygen or nitrogen and a -3 to a triply bonded nitrogen. Okay, so let's do this with methane going to CO2. Methane, we're going to pretend that the covalent bonds are ionic bonds. Okay, sorry, I forgot to say something. We have to give carbon whatever charge is needed to counterbalance the charges that we generated in the first step. All right. So we make each hydrogen an H+, like we did, like it tells us to do there in step 1. Overall, methane is a neutral compound. That must mean that carbon is 4- to compensate for the charges of the hydrogens that surround it. All right, it's transitioning to CO2. All right, so we're going to give a -2 to each doubly bonded O or N. So an O2- here, an O2- here, and that must mean that to counterbalance this, CO2, remember, is a neutral compound. That must mean that carbon is 4+. Okay, all right. So the conversion of methane to CO2, we say, is an oxidation reaction because there's an increase in the oxidation state at carbon from -4 to +4. Okay, and we can treat a variety of reactions that way. All right, so let's look at a few examples. To determine if an organic transformation is oxidation, reduction, or neither, determine the oxidation state for all of the carbons that undergo a chemical change, and then see what happens to the total oxidation number. Okay, if it increases, that's an oxidation. If the total number, oxidation number of carbon decreases, that's a reduction. And if it doesn't change, that means it's neither. Okay, so we're going to look at methane going to chloromethane, methane going to methyl lithium, and cyclohexene going to this compound over here known as cyclohexanone. All right, so we did methane in the previous problem. It's 4-. Let's now do chloromethane. Okay, so we're going to make all of the bonds into ionic bonds, H+, 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 Cl-, plus, minus, that adds up to be +2. That must mean that carbon has to be -2. All right, so when carbon goes from -4 to -2, that is an increase in the oxidation number at carbon. Therefore, we're going to call this an oxidation. All right, let's look at the next one. Methane to methyl lithium. Methane is still going to have carbon at -4. All right, when we turn the covalent bonds into ionic bonds, we get plus, 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 plus. So we have 4 pluses surrounding the carbon. Methyl lithium is a neutral compound. Therefore, the carbon oxidation state is -4. During this transformation, carbon's oxidation state went from -4 to -4. In other words, it didn't change. Therefore, we're going to classify this reaction as neither. It is not an oxidation or a reduction. All right, and the last one. Let's look at the carbons that change. We have to think about the fact that this bond line diagram has some hidden hydrogens. Okay, and that's an important consideration. We always draw these as bond line diagrams, but you can't forget that there are hydrogens there. All right, so those 2 carbons there are undergoing some sort of chemical change. There are no changes at these carbons over here. So we have to look at all the carbons that are undergoing a chemical change. All right. So this CH bond is going to be an H+. The other CH bond is going to be an H+. We're going to consider that the bonds to carbon are covalent bonds, so we're not going to ionize them. Okay, we're going to keep them as covalent bonds. All right. So this carbon has to be -1 to counterbalance the hydrogen there. This carbon here needs to be -1 as well. So when we add all the oxidation numbers of the carbons involved in the reactants, it turns out to be -2. -1 plus -1 equals -2. All right. Here, oxygen, the C double bond O is going to be an O2-. That means this carbon must be a 2+. All right, the 2 hydrogens, they're each going to be 2 pluses, so this has to be 2-. When we add +2 and -2 together, we get 0, so the sum of the carbons that change is 0. Our net total oxidation number at carbons goes from -2 to 0. Therefore, we have an oxidation. That is an increase in the oxidation number. -2 is going to 0. It's increasing in the oxidation number. All right, let's look at these. We'll do this one as a problem. Okay, so one of them you can do, the 2 on the left you can do the easy way. And the 2 on the right, it's not going to be so obvious, so you're going to have to do a calculation. All right, so the first one, we can see that we have the only difference between the reactants and the products is the presence of an oxygen. That's an obvious oxidation. All right, if we look here, the difference between the reactants and the products are these 2 hydrogen atoms. This is adding H2. Therefore, that's a reduction, but let's just calculate it for fun. All right, so 2- for the oxygen. When we ionize it, that must mean this carbon is 2+. It looks exactly like it did in the previous problem. Okay, when we ionize the H and OH here, okay, their charges add up to be 0. That must mean this carbon is 0. Therefore, carbon plus 2 went to carbon 0, and that is a reduction. Okay, let's do the last 2. Okay, so this one we've done before. The product is the same as it was in the previous one, but we need to change the reactants. Okay, so hydrogen, H+, bromine, Br-, plus, minus, equals 0. Therefore, the carbon isn't going to have a charge either. Carbon 0 goes to carbon plus 2. Therefore, we have an oxidation. All right. In this last one, it's kind of hard to see this one, but let's look at it. The starting material is the same as the starting material in a previous example. We'll just do it again here for completeness. H is H+. That means carbon is -1. And this other carbon looks exactly like it, right? So the sum of the atoms that are the carbons that are being changed is -2. Two negative ones added together is -2. All right, and the product, going to ionize the two substituents there, H at plus and Cl minus. These charges counterbalance. That must mean this carbon is 0. Similar thing is going to happen here. H plus. I'll just go the long way here. OH minus, a plus and a minus counterbalance. Therefore, the carbon is 0. When we add 0 and 0 together, we get 0. Carbon -2 becomes carbon 0. Thus, this is an oxidation.